Hello all, let's start with our today's DSA journey with this amazing visualizer. Use this link to get a 7-day free trial. Let's start with our DSA and today's important question, which is largest rectangle in a histogram. Okay, given an array of bar height representing a histogram where each of the bar has width 1, return the area of the largest rectangle that can be found within the histogram. Okay, so this is our input, this is our output. How could we get that? So first, I don't know what is happened to my escalator. If anyone knows how could I make it good, then just tell me. So not this one, this one. So we are given this one. So 2, 1, simply like 2, 1. So these all are the heights. All are the heights. These all are the heights. 2, 1, 5, 6, 2, 3. So these all are the heights, and every width is, we have to find the largest rectangle. Okay, so what is it want to say? So it just want to say that we have to calculate the largest area. So what can be our area? So for this I just copying this. I am just copying this thing. Okay, so this is our main histogram. So what is the area? So we can easily say area like let's take a different color like this one. I don't know the color. So this could be a area. Don't go to this one. This height 5 and the width is 2. Okay, this could be our area. Okay, and if I go to another color, this could be a area. This could be a area. So 2 and 2. Okay, also this could be a not this could be a area. So every height is same, or every height is same or equal. Okay, so if the height is greater than the height, so what is the lowest here in this green box is 2. So the height of the green box is 2. What is the lowest in this orange box? This orange box, the height is lowest is 2, so we take 2. What is the lowest in this pink box? Let's suppose take is a pink, the height is 5. Okay, so take another color, or rather I don't have this blue. So we can, okay, we can take everything from here till here. So this one, so the height will become 1. For the blue, the height will become 1 and the width become the whole array, which is nothing but 336. For this red one, the height will become 5 and the width will become 2. For this orange one, the height will become 2 and the width will also become 2. For this green one, the height will be 4. Okay, among all of this, so among all of this, which is the best one? This is, because this is 10, everything is less than. So we have to return this. We have to return this one. We have to return, actually return the area. If I am not wrong, in the question we have to return our area. Yes, we have to return our area. You can easily see it here. So this is our actually given height 2 1 5 6 3 2. This 10 we have to find the area which is maximum, okay, using this way. But the thing is, how could we get it? Okay, so first take one thing, just move it a little bit upper. Take this one. What is this? I need the normal one. The Excalibur having problems. So we actually make valid rectangle. Okay. Okay. For this 5, let's take an example. For this 5, can we go to the left side? No. Why? Because we have a value which is very less than current one. Okay, we have a value which is very less than this current one. Can we go to the right side? Yes, simple, because this value is either greater or equal. The value is greater or equal. But if you go a value is lower, then we can't. So for this 2, the value should be greater. This value should be greater. This 5 is also greater. Okay. But for this 2, the left side is empty and the right side there is nothing because the 1 is here. So these 2 only become height when the width is only 1. But this one can be a height of 1 with the whole length of the array. How? Because every element, this 5, this 2, this 6, this 3, this 2, everything has a size which is greater than the current value. Okay, so this current value 1 is somehow greater, is less than to every value, and every value respect to this one is actually greater. So for this 5 also, this left side is lower, but for the right side it is greater. So we can easily take a rectangle like this. Easily take a rectangle like this. So we can't take lower values. We always have to take the greater value which is very near to each other. So for these two, we can't consider this 5 because a 1 which is lower than 2 in between them. For this 3, we cannot take this 6 because 1, 2 is here which is not greater than 3. So this 2 is less than 3. Okay, 2 is less than 3, so we cannot take this 6. We cannot take this 6 for this value 3. So we are using this similar approach here. But how? We can use simple two loops to calculate each and every value. So what is our uh, condition for not selecting a value? The condition for not selecting any value is, like for this 2, we are not selecting this 1 which is lower. So suppose a value of I, okay, if the value of I, let's suppose the current I is at 5, okay, and there is a value which is a current J. So suppose J at 6. So can we take this 6 for this 5? Yes. So if the J is greater than, but if it is a 5, if the size of this is 5, we can easily take, because the similar element or the similar size we can make a rectangle also, like this example. Let's suppose this is our So this is our like 2 2, okay, 2 2 this one. So we can easily take this 3 2 and make a rectangle, okay, a rectangle or square or anything, okay. So we can easily take this 3 2. So for that reason we are using this equal to. So if we anytime got this, it simply means we got it. We got the element. But or we take the element, not got the element, we take the element to create a rectangle. But if any chance this I is become greater than j, then we just don't take anything. Just don't take anything. Okay. But how could we do that? We can do it using a to loop. So first let's visualize it. Okay. So latest rectangle fully inside the bar. Key observation: any candidate rectangle is capped by its shortest bar. So for each bar, go the left and right while the neighbors at least are as tall. Okay, so our condition is just taking this. So for anything, for any bar, for any bar, we go towards till the left, we go right, okay, and every time till we reach this index. So until, let's suppose it is I, okay, and we just go here using j. Let's suppose we can easily use it in two loop, okay. So if anyhow arr of I is become greater than arr of j, okay, or arr of I is become greater than arr of k. So for this condition, this 5 is greater, okay, we can, the loop breaks here, the loop breaks here, okay. We just don't take, we just don't take, and what we take, we just count. So for this I, which is currently at the bar 5, go towards left and count that if if any value is less than our index or not, okay. So our condition will be little bit changed. So if this happen, so if arr of I is less than equal to arr of j, so if we are going for this condition, we are going towards leftwards, and somehow we are getting a value greater than or equal to 5, okay. So till we get that value, we are using a counter and we just increase it so that we can calculate every value or every bar towards left. And similarly here also we are just increase our count. So for we are increasing the k, we are increasing our k, and we are increasing it till we get a lower value, and we just count every value of every bar, okay. And our answer should become our simple, our current bar height into this count. So our area would become arr of I into this count. So this count actually calculate every bar of both side, and the arr of I is nothing but this 5, okay. So our bar height, so every time we have to take this bar, suppose this bar, so height is always 5, but we have to check the width, which is nothing but the count, okay. So same thing here for this two, we cannot go left portion, we cannot go right portion, because both in the right portion there is a lower value, but in the left portion it doesn't have any value, so we don't consider it. But for this one, the left, we can got the left till 2, and we can go to the right, because every value in the right is greater than 1, every value. For this 5, the left is 1, we cannot go, but the right is 6, so we go. So for this 6, it is the highest, so we can't go there. But for this 2, the height which we get is easily till the 5, because 5 is greater than 2, 6 is greater than 2, 2 is equal to 2, and the 3 is greater than 2. So we can easily get this size. Okay, and for this 3 we get a only 3. So this is our best. So let's write the pseudocode here. So we are getting nothing but a function with like heights h, which is an array. So for I at the starting from 0 towards n minus 1, or take a maximum, or let's take maximum at the starting as 0, okay, which will be our answer. Then side we take two things, L starting from I, and also R is also starting from I plus 1. Okay, so L also start from I, and R also start from I. We just take two variables. This is for two loops. While L is greater than 0 and h of L minus 1, h of L minus 1 is greater than equal to h of I. Just simply L minus minus and just copy it. R is greater than n minus 1, or not greater, it is less than n minus 1, plus 1 is greater equal to R. So for this case, R plus plus, and at the end calculate the answer. So let's suppose take a area which is nothing but h of I into the count. And what is the count here? Count is the size. Okay, so it is nothing but R minus L plus 1. Just take the maximum, which is max of the maximum and the area. You just take the maximum area and return the maximum. Return the maximum. So actually, so this is our, so this is our code. And okay, just somehow take the code and write from, what is 6 calendar, what happened to this Excalibur? I don't know. So let's delete it. This is our bars. So in any condition, this is our condition. I suppose this is our I. We take one L pointer towards this and one R pointer toward this, and when we simply get, so we can easily got it. Just let me remove this one. So we are at 2. So when you go to the left, the L ends here, and you go to the right, the R ends here. Okay, this is our goal. So this 2 is the height, simple, and this R minus L plus 1, because it is a zero base indexing, so this will be our width. Okay, so R minus L plus 1 is our width, and this bar is height. So we just do the same thing here. Okay, let's just write the code. First take the size, which is nothing but height, size. Then we just take an answer at the starting, which is 0. Largest rectangle area, so take max area as our answer. So do a for loop from the starting towards the end, and inside the for loop we have to take 2 pointers, like one is L, which is going to the left direction, and another one is R, which is going toward the right direction, but everything started from this current index. Why we started from current index? Because when we start the thing from the current index, we index also, and for that current index we have to calculate our value, because we have to include that current index also. Okay, so first go to the left, so take a while loop. Our L is still the zeroth index. The height of L minus 1 is greater than equal to height height of L. Okay, just do L minus minus, and similarly go to the left when the right is n minus 1. Why we take n minus 1? Because we are calculating with the next value. So heights of r plus 1, because of this r plus 1, so we don't reach the last index and calculate for the index out of the bound, we use this r plus 1. So it greater than equal to heights of r. Okay, so simply do r plus plus, and now calculate the area, which is nothing but, first we have to take the height, and the height is heights of height. Okay, and now the width, height into width, so width is nothing but r minus L plus 1, and calculate the max area. Max area is nothing but max of max area and area. Okay, and at the end return area. So just not area, not area, at the end return max area, at the end return max area. So wrong answer. Okay, we are getting a wrong answer. So it should be less than, because r should be less than n minus 1, not greater. So that's why the condition is failing. R is greater than. Okay, it give us a wrong answer. Thus it doesn't support this. Let's do a minus. But it should not give us a wrong answer. It generally gives us a wrong answer. So maybe we do a mistake somewhere. Mhm. Let me check. We make a big tick. This should be I. This should be I. Why? Because the I should be same. From the I we have to calculate every L. Because we change our L. Because we change our L every time. Because L is great. L is getting minus minus, R is getting plus plus. This should be I. But why this work? This should be I. This should be I. There's a lot of problem while solving a brute force. I don't know what happened to the optimal. Yes, yes, for few cases we got a TLA. Wrong answer should not be. TLA is good, not the wrong answers. So let's do the optimize approach. So previous approach takes big O of n square of time and big O of one space. Okay. So now monotonic stack increase the time bars will wait on the stack while height rises. A shorter bar arrive means every taller waits. Now the right wall. Pop it and settle its rectangle. So first we push it, okay. But then we got 1 and 1 is smaller than 2. So we just pop it. Because the 1 is smaller than 2, we cannot take the 2 here. So we take that 1. Okay. So we take that 1. We, because the 5 is greater, it can be, we can store this 5 also. And store the 6 also because 6 is also greater than the 5. Okay. Compare with the top. Compare with the top. But after 6 it is 2. We cannot get it. So calculate it. 2 is less than 5. So we just take the 5 and calculate it. And we can insert our 2 here. Insert our 3 here. So after that, when nothing's left in the stack, just take that 3. Just take that 3. Okay, and calculate it according to, take the 2 and calculate it. Now take the 1 and calculate it. So we got our best answer. So just write down the code here, which is nothing but function which takes h. Let's take a stack which is nothing but an empty stack, and go to the every element. You increase through the array. You not increase, going to every element you get into the heights array. Okay, to n minus 1, take the every element, and while every time the current index, if the current index is less than the, take it as st. So while this current index is always less than the top, if any time it is less than the top, so if the top element is less than this, just pop the element. Okay, we have to pop the element, but before popping we have to calculate our width. So you can easily got it here, like when we put our index into the stack, the current distance, check it here, uh, not this one, here, see, uh, go to this two, no, yes, this two. Okay, we insert it. Now we got into 2. the 2 is less. Okay, so I pop the top element. The value of the top is 3, and what is the current index? 4. So 4 minus 3, 1. You can clearly get the width 1. Okay, so calculate it here 5. So the index of 5 is 2, and what is our current index? 4. So now 2 is less than 5, 2 is actually less than 5, and this current index I at 4, it is at 4, and the highest value in the stack, it is actually at 2. So 4 minus 2 is 2, and the this is the actual height, actual width, not height width. And what is the height? Height is nothing but the stack top, the value of the stack top. So calculate the area. So I minus st dot top. So this is our width. So now we have to calculate the height. We got our width. So height is nothing but the stack top element. If we just clearly see it here, the current stack top value is 5, and this 5 is actually our height. We got the width using it, and now we need the height, which is nothing but h of st dot top. Okay, so this is our height. Now calculate the max area, although we don't initialize it here. The max area is nothing but 0. So the max area is equal to max of area and area, and pop the element. So st dot pop. So just pop the element, and when everything is done, the pop, the push, the done, we have to push something. So what we are pushing here? We are just pushing the I. At the end, after calculating the value, we just push our I, which is nothing but the answer, which is nothing but actually the index, not the answer. Answer is max array. So return max area. So this is our pseudocode. I just don't want to go to Excalibur because I don't know. Okay, I got it. Condition while st and the stack should be not empty before we inserting anything, or we popping anything, not inserting. We can insert anything when the stack is also empty, but we actually pop element when the stack is not empty. So this is the actual condition. Okay, it take time so much. I don't know why it takes so much time, but we can go here and solve it because of, can we store it here? Just got messed up here. I don't know it, why everything going leftwards. Let's go to another one. Actually my internet goes. The- My internet goes. Just my internet comes. I was uh, busy while explaining the solution. Actually my internet goes. So let's just forget. Let's just take it and just solve it here. Okay. Uh, can we go it here? So this is our pseudocode. Okay, we will use tl. So this is our pseudocode, and we have to implement this pseudocode. So first take the size, which is nothing but uh, we are using this calculating this size every time to ensure that not every time you calculate it one time and store it. Okay, so take a stack which is nothing but integer st and answer which is a max area 0 int I equal to 0 I less than n I plus plus for every for every element we have to check at the first. What we have to check first, check the stack is empty or not. So our condition will be simple, while stack is empty or not. Stack is not empty. This is one of our condition. But because if the stack is empty, what should we pop from the stack? The stack is empty. We cannot take anything out of the stack. Also this condition. So the heights of current index is less than height of stack top. Height of stack top. So if this condition ever occurs, okay, if this condition occurs, first take the height of the rectangle, and the height is simply this one. But take the width. Okay, if in any condition, if in any condition the stack is empty, I I tell you why. So for this condition, the width is simply become I. Why? I just tell you. Okay, so I need a pencil. So this is our stack. Okay, this is 2, this is 2, and this is 1. So first we go to this index, we push this at 0 at the stack. Okay, and now we go to this next one. So when we go to this next one, we just encounter a low value. Okay, it is nothing but a low value. It is a very lower value. So when you actually encounter a lower value, just take the height, which is nothing but this one, and also the width. Okay, so when we actually take this width, we just got a 0 here, and when you pop this width, okay, sorry, when you pop it, there is nothing. So for this 2, there is nothing. Actually we can easily can we evaluate it. So if you go to here, actually you can clearly see first you got this 0 and we calculate the value. How? Because when we got here 0 here, we first push it because the array is now, just take it. So we just push the value, and we actually when we actually take the value from this array, we are actually at the last index. And when you are at the last index, there is no previous. So when we calculate the value using I minus st or top, our I is at 1. So 1 minus 0, okay, it will become 1. So for this reason, we are doing it here. So else nothing but I minus st dot top, and because it is a zero based indexing, we have to take minus 1. uh, why here it works? Because it doesn't matter, it doesn't so much matter here. and this should be st.top. uh, it is also my mistake. So our height will be st.top, but our width will be this. Why -1? Because it is a zero based indexing. So first we go here, we push 0 here, it goes here, and it will actually take a lower value. So 2 2 is actually greater than 1. So first the height will become this 2, and when first take moving it, and uh, we don't have any pointer here. So the height here, so when we remove it, we just got an empty array. So for that we are using this. Okay, so this is the simple formula. If anytime the stack become empty, we just take the width as this one, because we have to calculate our width with this index only. Because why only this index? Just because the stack become empty and we don't reach anything. Okay, so the condition actually occurs at the end. For 3, we just push it, pop it, and we just do everything. Yeah, everything. Just see it. We have currently have 1 in the array. We have currently have 1 in the stack. The 1. Okay, when we actually have only the 1, when we pop it, we don't have any values left in the stack. Okay, so what is our current value? Our current index is out of 3, which is 6. So our width becomes 6. So for this last one condition, we are using this. Otherwise, the value will become very different. Okay. So now calculate the area, which is nothing but height into simple, and the max area is equal to max area and area. Okay. And every time we calculate the max area, we just have to do one thing. We just have to pop the top element. Okay. And at the end, just return just return the max area. Answer. Okay, let's check where we do the mistake. Stack is not empty and height of I is less than height of st.top. Is okay. So we take the height, take the width, take the area, pop the top element. Okay. Now the thing is, where we make the mistake? Let me check. Actually, we are missing one condition here also, that if in time this will happen, so we are getting, so why we need this condition? So if we are actually having greater elements, so suppose our uh, bar will become 1 2, just see this bar. So if all of these are actually getting increases, so it continuously increasing, so every time we store the value. So at the end we have to calculate the total answer from here also. We have to calculate every answer from here. Okay. So for this reason we have to do this condition, that if any time the stack is not empty, also the heights, we know it matches the height condition, that the next height is greater than, but it reaches the end of the array. Okay, so then we have to pop some element from the end. Okay, it still give us a wrong answer, and I am still wondering. Well, it shouldn't. Actually, put the eye, the height of exterior top. Top eye is less than height of exterior top. Well, it is okay. This should become okay. Just give. Actually, we are doing two things wrong here. We have to pop it at the start. Why? Because if we don't pop it at the start, we don't get the width. And also we have to go towards n because we are calculating this condition. Yes. For this too, we have to pop at the first. Why? Why? Because to calculate the width. Just pop at the first. So this is our question. Largest rectangle in a histogram. So go. This is like big of in time complexity and space is big of n. Big of n time, big of n space. Simple as that. So this is the question, largest rectangle histogram. Go use this. Go and use this platform. Use my link, this link. Use this link. Get a 7-day free trial. Go use this link to get a 7-day free trial. Use this platform at dsa.chaicode.com. Thank you. Thank you very much.